Hello everyone to the start of the pre-calculus stream. Today we will be doing a continuation of polynomial expansions. More specifically, we're going to go over the binomial theorem, and instead of just looking at how to do it, we're going to look at why it works that way. So let's write out the binomial theorem. The binomial theorem can be written out as a plus b to the power of n equals the series of n as k approaches n starting from 0, the combination of n k and x minus k y k, and n of k is equal to n factorial over k factorial times n minus k factorial. So we looked at how this is represented. To take a quick example, if n it's a plus b equals 3, let's say this is the example, it looks something like yeah, it looks something like 3, 0, x 3 plus 3, 1, x2, y plus 3, 2, x, y squared plus 3, 3, y cubed. Now, if you look here, these things multiply out, and you just plug in 3 for here and 3 for there. Now, the binomial theorem is effectively an equation made out of what it's known as the Pascal's triangle. So this essentially is going to be the base thing that we got the concept of the binomial theorem from. So start with the number 1. Let's say we have a row of zeros and just 1 in the middle. But we make a new row, except we add these two numbers together, the next two numbers together, and it makes a new row underneath. We're gonna call the first row the 0th row, and call the second row the first row. Well, all these zeros make 0, 0, 0, whatever, but 0 when it reaches the 1, 0 plus 1 equals 1, and 1 plus 0 equals 1. 0, 0, 0. Can continue do the same thing that we did. 2, 0, 0 all the way through here, but 1 here, a 2 here, because it's 1 plus 1, another 1 here, and 0, 0. You don't actually, when you write this out, you don't actually need all these excessive zeros, but I'm just putting them here now to give you a sense of what it is actually like. Now, third row. We can keep going as long as we want. 3, 3, 1, 4. 1, 4, 6, 4, 1. Now, if you look here, or actually let's do one more pattern to show this better. 5, 1, 5, 10, 10, 5, 1. Now, if you look here, you can see the general pattern this follows. So, starting from the outermost numbers in each row are always the ones. And because the ones are always added to 0, they just create essentially a barrier of ones on the outer surface. Now, if you between there, well, in the case of 1, it's a bit different, but you can see that between, right next to the ones, exist the number of the row. So in the second row, we have 1, 2, 1. Third row, we have 1, 3, 1. Fourth row, this is 1, 4, 6, 4, 1, but next to the ones are the fourth. And for 5, we have 1, 5, 10, 10, 5, 1, with 5s being next to the ones. The answer to this is also kind of obvious. You always add 1 to the current number, and you started from 1 plus 1, so we keep going up by 1 each time you add to the respective row. Now, how this plays into the binomial theorem is that, well, this might be easier if we take a quick example. So let's pull up the binomial theorem again. Let's take the binomial theorem of a plus b 2. This becomes a plus b squared plus, no, a squared plus, this one's more obvious. We don't actually need the binomial term for it because it's, well, it's just a squared plus ab plus ab plus bb. So this becomes ab 2ab and a b squared. If you look here, the coefficients for this are equal to the second row of the Pascal's triangle, which is the same as the number we used to do here. And using the same logic, this applies to 3 as well. So let's use this example we already have. We need to solve the combinatorics, but it's pretty simple. 3 factorial over 3 factorial is 1, 1, so x3 plus 3 factorial over 2 factorial is 3, so x squared y plus 3xy squared plus y cubed. And if you look here, Pascal's triangle contains the exact same coefficients. Even if b was reduced to a normal integer, by multiplying it to the coefficient, you could easily find the answer that you have here. Now, the Pascal's triangle can be used as an alternative to the binomial theorem. After all, it serves the purpose of giving you the right numbers. However, the problem with it is that you need to write out this whole thing each time you want to use it. So it is much more efficient to use the binomial theorem. So let's look at why these two are related. This will be probably the main concept we cover for today. So what is this n of k thing? So this format is actually used in combinations or combinatory for, let's say, probability calculations and such. Essentially, this essentially gives you the number of possible outcomes that you can have with this. To give you a more direct example of this, word by word example would be, so let's say you have A, B, and C, right? How many different ways could you list out A, B, and C? Or how many different things could you make with A, or how many groups of ABC could you make with, well, 2 spots? You could have AB, BC, or CA, right? Or AC, depending on how you list them. But CB, AC, and BA are effectively the same thing, right? In this case, we're key thing to mention is that we're not talking about the order. We're talking about purely about what is in this group. So abiding to this, it lists out a total of 3 different possibilities, right? If order mattered, there might be more. Like we could have, we would have 6, but so let's look at the formula of combinations and permutations again. We went over this in the previous video, but to show them again, combinations are n r n n minus r factorial. Permutations are right. So we have this here, right? So let's look at the difference between these. Combination looks, well, it doesn't just look similar. Besides r being k, that's why I said r and k were interchangeable earlier. It's the exact same as the formula we use here. Now, you have to understand why we need to use combinations instead of permutations. So, what's the key difference between here? I explained that permutation cares about order and combinations doesn't have order, but what does this r factorial down here have to do with it? Well, by having the r factorial here, it divides the number of possibilities by already that you present by the number of stuff that you have, so it gets rid of all this extra stuff that you actually have. Now, let's look at this. So let's go back to this as an example, right? This specific example. What this is essentially saying is, how many ways can you list, or how many outcomes can you get if you have 0 spots and 3 different numbers? Well, if you have nothing, you can't place anything in there, right? So no matter what you try to do, you can't do anything besides just leave out a 0. So there's one possibility. In this case, it gives you 1 spot, this thing on the bottom, gives you 1 spot and 3 different letters, 3 different numbers. You can get 3 distinct different outcomes. Here you have 2 spots, 3. We already showed that over here. Through this, we can only get 3 outcomes from here. And 3, 3, well, 3 spots with 3 numbers. You gotta put them all in, right? You don't have any other choice. So 1 again here. You'll see that this lines up with Pascal's triangle. The reason this type of thing matters is because when you multiply out these polynomials, like this, each time you multiply them, they are effectively more or less, the reason they get these like big coefficients is because you end up with multiple numbers of these, and for each one, you're essentially counting for how many times it can occur. Those two. Let's try to do an example of something bigger that should help us visualize this combinatory thing even better. So let's bring up this whole thing again. This time, in some ways, if we have the Pascal's triangle already written out, it's a lot easier. So 5. Well, to do this, it's just x5 plus 5x4 y plus 10 x3 y2 plus 10 x2 y3 plus 5 x y4 plus x to the fifth. Uh, that came out much easier, right? It was a lot faster than actually doing the binomial theorem through it, but again, you'd need to have written this out, and because you can't do this all the time, it's usually faster to just use the binomial theorem. Now, it's important to note here that in this case, what this 10 means is that you got the coefficient x plus 2 from multiplying a plus b to the fifth power 10 times. You got this total coefficient 10 times because there were 10 different possibilities for it for 10x third y squared to occur. That is why the coefficient is effectively 10. That's probably where we're going to end the stream at for today. So thank you for watching. Today was more or less just a expansion on the details of the binomial theorem. We're going to be moving on to more combinatorics, and we're going to look over at probability again.